Example 2 is really just a reworking of example 1 from the last video, except we're doing it on Jupiter, where gravity is a little bit stronger, actually quite a bit stronger, instead of on Earth. So on Earth, the acceleration due to gravity is 9.8 meters per second squared. On Jupiter, which is a much bigger planet, acceleration due to gravity is quite a bit bigger. It's 23.6 approximately meters per second squared. So honestly, if you felt really good about example 1, you can probably skip over example 2. If you feel like you might need a little bit more practice for that kind of thing, feel free to watch example 2 here. Otherwise, if you did feel good about it, go ahead and skip ahead to example 3. All right, so for example 2, the equation we're going to use, again, let's put the standard form, or not the standard form, but the original equation up here. So it's negative 1/2 times the acceleration due to gravity times t squared plus the initial velocity times t plus the initial height. And that is going to give us the equation here. So for this one, everything's going to be the same, except we're going to be changing the acceleration due to gravity. So the initial velocity is going to be the same, and the initial height is going to be the same. It's just that we're changing the acceleration due to gravity because we're doing this on Jupiter now. So then what we're going to have is the position with respect to time is equal to negative 1/2 times the acceleration due to gravity, which is 23.6 times times t squared, then plus the initial velocity, which from the last video was 19.6 meters per second times t, then plus the initial height was 13.8 from example 1. So then we want to simplify this a little bit. We get the position with respect to time is equal to, then half of 23.6 is going to be 11.8, so that's negative 11.8 t squared plus 19.6 times t plus 13.8. So that is going to be the equation for this height. Now the y-intercept, again, is going to be 13.8. And then, again, that's when you plug in 0 for t. All this stuff will drop out, and you'll just be left with the initial height of 13.8. So that's the same as example 1. Initial height is the same. Now the t-intercepts are going to be different. Because since the gravity is stronger, it's going to have a greater pull on the rocket, and so it's going to pull it down to the Earth, to Jupiter a lot faster. So if we go through and work through the quadratic formula here, we're going to get x equals negative b, which is negative 19.6, plus or minus the square root of b squared, so that's 19.6 squared, minus 4 times a, which is negative 11.8, times c, which is 13.8, all over 2 times a, which is 2 times negative 11.8. Work through all of that, and you should get t is equal to negative 0.5 approximately, and t is equal to about 2.2. Now again, one of these is happening before we actually launch it. So this negative time that's happening, that's saying that it's going to hit the ground half a second before we launch it. Well, again, that makes no sense in the context of the problem, so we're going to throw that one out. And so what we see here is that it's going to hit the ground after 2.2 seconds. Now, if you remember from the last one, when we did this on Earth, it hit the ground after 4.6 seconds. So on Earth, if we launch it from 13.8 meters up off the ground at an initial velocity of 19.6 meters, it's going to take 4.6 seconds to hit the ground. On Jupiter, doing the exact same thing, it would take 2.2 seconds to hit the ground. So it would be less than half of the time spent in the air if this were on Jupiter rather than on Earth. All right, let's look at the vertex then. So the t-coordinate of the vertex, that's going to be found by negative b over 2a. So that's negative 19.6 over 2 times negative 11.8. And if you work that out, that's going to give you 0.8. So that is the time that it will hit its highest point. And then if we want the y-coordinate, we're just going to plug in 0.8. And if you work through all that, you should get a height of 21.9. So the vertex then is going to be at 0.8 and 21.9 for the y value. So to graph this, again, let's scale the y-axis. I'm going to use the same scale as we did last time. So 8, 16, and then we'll put 24 there, and then we'll leave the x-axis just the same with 1, 2, 3, 4, and so on. Okay, so we have it hitting the ground half a second before we launch it, which again, we can ignore that, but for the purposes of graphing, we'll put it there. It's going to have a y-intercept of 13.8, and the vertex is going to be at 0.8 and then 21.9. Will be approximate here. It's going to be somewhere around there. And then the other place it hits the t-axis, the place that it hits the ground, is going to be at 2.2 seconds, so that's just after 2, right about there. So graph this parabola. And again, really all we care about is this part from the launch going up and then coming back down to when it hits the ground. All the rest of it, this is underneath the ground, so that obviously doesn't matter. And this is happening before we even launch it, so that doesn't matter. All we care about is this part right here. So you can see from the graphs, if we compare them, this one goes quite a bit higher and is in the air quite a bit longer, and this one quite a bit less because Jupiter has more gravity. All right, example 3, we're going to do something on the moon, except this one's going to be a little bit different because instead of launching something up into the air, we're just going to drop it. So we're just going to be holding something, and then you let go of it, and then see how long it takes to hit the ground. So what that means, if you think about the initial velocity here, if I'm holding something and then I let go of it, how fast is it moving at the instant that I let go of it? Well, at the instant I let go of it, it's not moving at all. So it starts moving once I let go of it, but at the very instant when I take my hands off of it, it is motionless. And then when I let go of it, then it starts moving. And so the initial velocity here, the velocity at time 0 is 0. And so that means our middle term is going to be 0. All right, let's work through this then. So, well, in 1971, on the Apollo 15 mission, astronaut David Scott dropped a feather and a hammer on the moon to show that with negligible wind resistance, everything falls at the same rate. So, you know, if you were on Earth to take a hammer and a feather and drop them, the hammer would hit the ground first because the feather would get caught up in the air and it would kind of float down on the air. But on the moon, there's virtually no atmosphere. There's a little bit, but it's not really much of anything. And so if you were to drop, well, and we did this experiment, and if you drop a feather and a hammer on the moon, since there's virtually no air on the moon, they fall at exactly the same rate. They hit the ground at the same time. And so let's say that he dropped these two things from 1 meter. So that's about, you know, the height that you would drop something from. And then let's find how long it took for them to hit the lunar surface. So we're going to graph height versus time. So let's first find the equation, then we'll find the intercepts and then graph it. So the position with respect to time is going to be equal to -1/2 times the acceleration due to gravity, which on the moon, since the moon is so much smaller than Earth, it has a much smaller gravitational influence. And so the moon's gravity will pull things down at a rate of 1.6 meters per second squared. So we're going to have that times t squared. Then add to that the initial velocity times t. Well, remember, if we're dropping this, then the initial velocity is 0. So that's going to be 0 times t plus the initial height, which was 1 meter. So s of t then is equal to, that's going to be -0.8 t squared plus 1. And let's look at getting the intercepts now. So we could, again, use the quadratic formula here. Actually, I'm going to do something different, though. So if we're wanting to find the t-intercepts, that's where the y value is 0. So let's say this is 0 equals -0.8 t squared plus 1. So again, you could use the quadratic formula, but what I'm going to do here is actually, since we don't have the t here, we can solve this just by taking the square root. So I'm going to subtract 1 from both sides, and then divide by -0.8. And then what we're going to get from that is, let's see, t squared is equal to 1.25, and then square root both sides. And we get that t is equal to plus or minus the square root of 1.25, which is approximately 1.1. And we'll just round it off to 1.1. So that means that this the hammer and the feather are going to hit the ground 1.1 seconds after being dropped. And again, there's this kind of part that we don't need. It's also saying that it's going to hit the ground 1.1 seconds before it's dropped, which is obviously not going to be the case. So what we'll do here, because we've got values that are quite a bit smaller, let's say that this is 1 and that this is 1. So we're going to divide this up into very small increments here. So then the y-intercept is 1, so that's going to be up here. And then the t-intercepts are 1.1. So we'll just extend this on a little bit more. So we hit the ground 1.1 seconds after being dropped, and then also 1.1 seconds before being dropped. So this would be -1 here. And then so it's going to look something like this. Now again, we're going to ignore most of this graph. So all we care about is from when he drops it from a height of 1 to it falling down to the lunar surface after about 1.1 seconds. So again, this stuff down here, this is happening underneath the ground, so obviously we don't need to count anything that's happening underneath the ground. All of this is happening before it was even dropped, so we can get rid of all that. All we care about is from when it was dropped from 1 meter to when it comes down and hits the surface of the moon.